Let a0 be 2, a1 be 3. For n greater than 1, we define an to be 3 times an minus 1 plus 4 times an minus 2. Okay, for example, we have a0, a1, a2 would be defined by 3 times a1 plus 4 times a0. Okay, and we need to use strong induction to prove that for all natural number n, a sub n is 4 to the n plus minus 1 to the n. So this we call it P of n. P of n is this statement. Okay, so we do that by strong induction. So let's consider this separate first case and second case first, because it's defined by another formula for all n greater than 1. So n greater than equal to 2, we can use this formula. Okay, for n equal to 0, we need to show that P of 0 is true, right? So P of 0 is a0 equal to 4 to 0 plus minus 1 power 0. So a0 is, this is equivalent to a0 equal to 1 plus 1, so equal to 2. This is true because of definition of a0. So definition of a0 is a0 equal to 2. So P of 0, this statement is true by definition of a0. So now n equal to 1, we still need to consider it separately because it's defined by a separating formula, a1 equal to 3 by definition. So we need to show that P of 1 is true, meaning that we need to show that a sub 1 equal to 4 to the 1 plus minus 1 to the 1, right? We just replace P of n by P of 1, right? Okay, so a1 equal to this P of 1 says, right? So this one equal to 4 minus 1 equal to 3. So this means that P of 1 say a1 equal to 3. This is true again by definition of a1 equal to 3. So hypothesis says that for n equal to 1, P of 1 is true. Now let n be at least 1. Okay, so we need to suppose by we want to use it strong induction, right? Let n at least 1. Suppose that for all natural number k in between 0 to n, P of k is true. So P of k is true for any k between 0 and n. So 0, 1, 2, 3 until n, right? Meaning that a sub k is 4 to the k plus minus 1 to the k. So we call it the inductive hypothesis. So it's true for any k. P of k is true for any k between 0 and n. We need to show that P of n plus 1 is true. So we know that it's true from 0 to up to n, right? Including n. So we need to show that it's true for n plus 1. So P of n plus 1 say that a sub n plus 1 equal to 4 to the n plus 1 plus minus 1 to the n plus 1. Okay, so recall that we have n at least 1. Therefore, n plus 1 is at least 2. And we know that for n at least 2, a sub n is defined by this formula. 3 an minus 1 plus 4 an minus 2. So we can use this right here for an plus 1. So our n is at least 1. So this is at least 2. N plus 1 is at least 2, which is good for us to use this formula. A sub n plus 1 is 3 an plus 4 an minus 1. Now we can use inductive hypothesis for an and for an minus 1, because we know that P of k is true for any k between 0 and n. So it must be true for n, and it must be true for n minus 1. Okay, so P of n say that an equal to 4 to the n plus minus 1 to the n. This is by inductive hypothesis in case of n, right? And by inductive hypothesis for n minus 1, we know that a sub n minus 1 equal to 4 to the n minus 1 plus minus 1 to the n minus 1. This is true in this case n k equal to n minus 1. Okay, now we only need to do the computation. So we try to get the right hand side, right? We try to get 4 to the n plus 1 and minus 1 to the n plus 1. So the first step here is I just do the distributive. So 3 times this one, 3 times 4 to the n, plus 3 times minus 1 to the n, 4 times 4 to the n minus 1, 4 times minus 1 to the n minus 1. Okay, this equality is true because now I have 3 times 4 to the n for this first term. We want to get 4 to the n plus 1, therefore I multiply 4. I divide it by 4, so it's good. Nothing changed. Just multiply by 4 and divide it by 4. Okay, for the second term, we want to have n plus 1, right? Minus 1 to the n plus 1. So to get that, I multiply minus 1, and I multiply minus 1 one more time, so that this term will give exactly 1, so nothing changed. It's still 3 times minus 1 to the n. Okay, similarly, we can do that for this term. We want to have n plus 1. So we have 4 times 4 n minus 1, which is 4 to the n. We want 4 to the n plus 1, therefore I want to multiply 4. I divide it by 4. So this cancel out, we have, and nothing changed, right? But now, if we use associative, we know that this 2 will give us 4 to the n plus 1. What is what we want? Okay, similarly, for the last one, we want minus 1 to the n plus 1. Therefore, I multiply minus 1 square. So nothing changed, because minus 1 square equal to 1. This term is still here. Okay, at the end, we have 4 to the n plus 1. So like 3 over 4 right here. Minus 1 to the n plus 1. So multiply 3 minus 1. 4 to the n plus 1. Multiply 1 over 4. 4 times minus 1 to the n plus 1. So we good. So now we have 3 over 4, 1 over 4 of 4 to the n plus 1. So it is 3 over 4 plus 1 over 4 of 4 to the n plus 1. Here we have this common term, minus 1 to n plus 1. And we have minus 3 plus 4, which gives us 1 times 4 to the n plus 1, which is 4 to the n plus 1. Minus 1 to the n plus 1 times 1, which is this one. This values is the right hand side of p of n plus 1, which is this value. So we did show that a sub n plus 1 equal to 4 to the n plus 1 plus minus 1 to the n plus 1. And therefore, we did show that p of n plus 1 is true. By strong induction, we proved that for all natural number n, p of n is true. And we are done.